All right, and part 3, we're going to talk about proteins and enzymes, but first I forgot to do the on your own question here. So if we have plenty of glycerol available, how many fat molecules can be made from 15 fatty acid molecules? So if we know that 3 fatty acid molecules are needed for every lipid molecule, and it's telling us that a glycerol is not a problem. We don't have any lack of glycerols. How many lipid molecules can be made? So of course it'll just be 15 divided by 3, which would give us 5. We can make 5 lipid molecules from our 15 fatty acid molecules. Okay, so now we'll move on to proteins and enzymes. Proteins are also built from acids, specifically those called amino acids. There are only 20 different amino acids in our bodies, and all of the proteins that we use in our bodies are made from different combinations of these 20 amino acids. Each of these amino acids is linked together again through a dehydration reaction with something called a peptide bond. There we go. We have the definition of peptide bond is a bond that links amino acids together into a protein. The average amino acid has about 20 to 40 atoms, and then I think it's interesting to say that the simplest protein of all of life is 124 amino acids linked together. There's a schematic of the simplest protein that we know of called ribonuclease, and the different amino acids linked together to form that. And it's interesting, and the book points this out, from an evolution versus creation standpoint, to look at that when scientists want to say that life just came together in a pond, that just to form a simple protein takes 124 amino acids, which each of those amino acids having at least 20 atoms, for them all to be linked together just to form one protein that in itself is not alive. How far-fetched that is without a creator to put everything together for us. The book goes a little bit into examples of some of the names of the amino acids, things like lysine and glutamic acid and things. You don't need to know any of those names for the course. They're just there to give you some examples. Okay. So those proteins form, obviously the things that we think of being proteins are muscles in our body, but proteins also form another very important class of chemicals in our body that are called enzymes. And these enzymes act as catalysts for many of the chemical reactions that support our lives. Okay. Let's turn the page here. Okay. One example of an enzyme that maybe you have heard of, I'm going to pull out my notes here, okay, is lactose. Lactose is the sugar. Lactase is an enzyme that breaks down milk sugar. The sugars in milk are made from glucose and galactose linked together into a disaccharide called lactose. In order for our body to use this lactose, we need to be able to break it down into its separate components, glucose and galactose. In order to do that, we need this catalyst. We need this enzyme catalyst, which is called lactase. Most of us produce lactase. However, some people's bodies do not produce it. If they can't produce lactase, they can't break down the lactose, and then the lactose makes them sick. And, people have stomach pain, diarrhea, things like that after eating milk products, and it's often because their bodies don't produce that lactase. Okay. If you heard the debate between, raw milk and pasteurized milk and things like that, raw milk contains some amount of lactase in the milk itself. This is what also will cause part of what causes the milk to sour as it just sits over time, is the lactase starts to break down the lactose. But when you pasteurize that, you destroy those enzymes. So if somebody's body doesn't create this enzyme on their own, then they obviously can't break that down at all. Another enzyme that the book mentions that's important for life is sucrase. Sucrose, okay, is our table sugar that is made by linking glucose and fructose together. In order to break those apart so that we can use them in our body, we need this enzyme called sucrase that breaks apart sucrose. You'll see that ACE ending in a lot of enzymes, and it often correlates with the thing they're breaking down, as in lactase with lactose and sucrase with sucrose. Okay. Our book here gives us an example of the lock and key action of the enzyme sucrase. So showing how this sucrose, the disaccharide here, fits right into the sucrase enzyme. And then the enzyme acts as a catalyst in our hydrolysis reaction, or adding a water molecule to break these two monosaccharides apart into the simple glucose and fructose.